Okay, so what we're talking about in this video is energy conservation. And so this is in the grand scheme of quantifying the energetic state of a system. And so that's sort of our goal in general with this set of lectures on energy. So we want to quantify the energetic state of a system. That is our goal for these couple of videos. And so far, what we've developed is an idea of what kinetic energy is. So we have a change in kinetic energy that's equal to an amount of work done, and we know that that is a force over a certain distance, and we're using vector and calculus definitions to work through that. And we saw that our change in kinetic energy there, if all we're doing with our work is changing the kinetic energy of the system, then we have a 1/2 m final squared minus a 1/2 mv initial squared. And then if we have this definition of kinetic energy if an object starts from rest, which is just 1/2 mv squared if its initial velocity is 0. What we talked about last lecture, we came up with the formulation for the work done from a spring, and we saw that that was 1/2 the spring constant times the displacement, so the expansion or compression squared, and that came from the idea that we have this spring force from Hooke's law, which is just minus kx. Okay, so what we're talking about today is the idea of energy conservation. And really this is the idea that we can discuss energy that has been transferred to or from a system by a variety of different forces, and some of those are conservative forces and some of those are non-conservative forces. So let's think about that definition of conservative and non-conservative forces to begin with in this discussion. So when really coming up with a definition of what conservative and non-conservative forces is, essentially what we have is that for conservative forces, the work that has been put into the system can then be taken out of the system in some useful way. Work put in can be taken out. In a non-conservative force situation, what we have is that the force that puts work into the system, really that transfer of energy just goes into increasing the overall temperature of the system. So our work or our energy is basically converted to heat if we have a non-conservative force working on a system. So one important thing about conservative forces when we're talking about a force acting over a certain distance, it's really important to keep in mind that we have this distance or path variable in there when we're looking at our amount of work or energy transferred there. We have that path, and for conservative forces, we have the particular nice aspect of these systems where we have path independence. So what's that mean? That means that the net work done over a closed path is 0. So if you have only conservative forces acting on your system and you return to where you started after doing a certain amount of work and transferring a certain amount of energy to or from the system, then you're going to end up with, if it's a closed path, then your net work, the total energy that you transferred, is 0. Okay, so those are sort of basic ideas of what conservative and non-conservative forces are. We can start talking about examples of conservative and non-conservative forces. So we've already dealt with 2 types of forces so far in these lectures. One, when we first started talking about work, was gravity. And gravity is a conservative force. If you increase if you do work on an object and then increase the amount of energy by working with the force of gravity, then you can then get that energy right back out of it. This is the idea where if you throw a ball into the air, you do a certain amount of work on it, it increases the amount of energy that it has, and then gravity puts that work back right out of the system, and the ball falls downward. So that's energy that we can store using that force. And then the other force that we had talked about last lecture was the spring force. Similar to gravity, and we had talked about this, you can put energy into a system via a spring force and then take that energy right back out. So those two are examples of conservative forces. Now, thinking about non-conservative forces, we have these types of forces that you may be familiar with that cause things to get hot. And so the first one that usually comes to people's mind is friction. So if you rub your hands together, then you can warm your hands up, and that is using friction to increase the heat in your hands, and that is a non-conservative force. And so that doesn't have this path independence thing. You are converting energy to heat as you drag an object along a certain path, and if the path is longer versus shorter, you have converted more energy into heat, and you don't have that net zero when you get back to where you started. Another force that acts just like friction in terms of being non-conservative is drag. And really, on a very small scale, drag and friction are pretty much the same thing. But yeah, so if you have a drag force acting on an object that's moving through a fluid, right, so a plane or a submarine, let's say, that force is non-conservative. So you won't be able to get all of the energy out that you put in to move that object around if you have friction or drag. And so those are important things to keep in mind. What we're going to concentrate on for the rest of this video is going to be conservative forces, and we're going to come up with this quantification of how much work we've stored that then we can then take out later. Okay, so for conservative forces, essentially what we have is this idea that work can be stored as what we're going to call potential energy. Work can be stored as potential energy. So it's basically energy that we can do something with, right? We can put this work in, store energy in our system, and then take it out as long as we have a conservative force. And so we will denote potential energy as delta U. So this big capital U is our potential energy. That's a change in potential energy. So our change in potential energy is the opposite of the work done on a system there. So working with that definition there, we can then address our two examples of conservative forces and think about what exactly the change in potential energy looks like for each one of those conservative forces. So if we do something to the system using those forces, gravity or spring force, how much energy can we store in that system? So let's start with gravity. So going off of our definition of potential energy here, which is the opposite of the amount of work done to the system, we can then just use that in our dy. And here I'm making the assumption that we're only dealing with one dimension, right? We're going directly up. Our y direction is altitude, essentially. And so we have our force from gravity that is going to act in that direction. And so if we just integrate this, we know that force from gravity is mass times our gravitational constant. And so that is acting downward. And so if the positive y direction is upward, then we have a minus mg, and that's over the integral of dy. And so basically what we just need to see is that our minus signs cancel, and we have an mg times a change in height. So that means that the potential energy over here from gravity increases with height. And it's an important thing in terms of all of these energy situations to come up with a reference point, an energy equals 0 or a potential energy equals 0 reference point. So if we make our reference point at some arbitrary y equals 0, and that could be the ground, it could be your hand if you're throwing a ball into the air, that kind of thing, then we can define the potential energy from gravity at any certain height as equal to the mass of your object or system times the gravitational constant times the y position of your system from that y equals 0. So then we have this definition of the potential energy from gravity. Okay, the other conservative force that we talked about was the spring force. And you'll remember that this force changes with compression or expansion of a spring. And if we start again at our delta U equals minus W, then we can then have our minus F dx here, where x is going to be the position of our spring. So we're either compressing or expanding it. And so we know that basically that spring force fights against whatever the change that we're putting in it is. And so we have a minus k for the spring force there, and then we're integrating over the distance that it's been compressed or expanded times our dx here. So just like when we were dealing with work, this becomes a relatively easy integral to solve, and we have our change in potential energy from a spring, which is 1/2 kx final squared minus 1/2 kx initial squared. In terms of signs, it's important to note that this is the opposite of the last video that we saw. The potential energy is the opposite of the work done. So you just want to keep that in mind, keeping your signs straight. Again, we can set our reference equal to a non-expanded or compressed spring. So our reference is going to be x equals 0. And so that's our relaxed spring there. And then we can say that the energy that we store, the potential energy that we store in a spring, is equal to 1/2 kx squared, where x is the compression or expansion. And that's the amount of energy that we can get out of this spring after we compress or expand it. And so then you have, for our two conservative forces that we've talked about, you have the potential energy that you can get from either one of them. Okay, so we can put all of this into context of everything we've been talking about so far in these lectures here, especially if we have conservative forces. And we can start talking about potential energy, work, and its branch over to the kinetic energy that we have in a system, right? So if you think about this in terms of work stored or work spent somewhere, then we can talk about potential and kinetic energy. So if potential energy is work stored in a system, so delta U equals minus W, and kinetic energy is work spent on motion. So our change in kinetic energy is work spent on motion, so we get an object moving. Then it stands to reason that we can relate these two things together if we have a system where nothing else is acting on it. So if there's no external forces being applied to your system, then there's no additional work that we're playing around with. And if all of the forces are conservative, then we're basically just transferring energy from potential to kinetic energy, because we're not losing any energy to heat there. And so we say that if we have an isolated system with conservative forces, then we can call the total energy constant, because we're not losing energy or gaining energy from anything. So our total energy is constant, which means any change in potential energy that we have in our system comes from a change in kinetic energy. And we can break this up a little bit more to get to a point where we can start to relate our energy in different states of our system. So thinking about the context of a ball being thrown into the air, we can talk about the total energy in the system when the ball is all the way up at its maximum height versus the total energy in our system right before the ball hits my hand as it's falling. And so we can talk about an energy in state 2, which is equal to some energy in state 1, right? And so just as easily, we can define that by a combination of kinetic and potential energy, which is equal to a combination of kinetic and potential energy at some other time. Now, these might not be, K1 doesn't necessarily have to be equal to K2, right? But the total K plus U is going to be equal at every different state in the system, as long as you have an isolated system with conservative forces. And just in terms of terminology here, we call this combination of kinetic and potential energy mechanical energy. So that's going to be something that we return to pretty often. And build upon is this idea of our final energetic state equaling our initial energetic state. And one thing that's really important here is that this has no time dependence. So it doesn't matter how long it takes to get from one energetic state to another. We can still relate those things to each other as long as we have this isolated system with conservative forces. And that's actually a really powerful thing in solving all of our problems. You could go back and resolve all of the kinematics problems that you've done so far in this course, or many of them, using these mechanical or these energetic arguments, and then be able to completely take out the time variable as long as you know the distance traveled.